Okay, guys, welcome to the class. So, what's the time? 30 minutes. My phone is out of power, so okay, I'll use that time. So let's review what did we learn last night. So last night we basically learned a method to find the inverse of a matrix, which is set as a second method to find the inverse. Basically, you use you find the adjugate, which is a matrix of the algebraic factors, and then you divide that by determinant to find the inverse, right? So last night we learned the method to find the inverse. So that's a second method. So let's just practice an example to review the method we learned. So anyone give me maybe 9 numbers?
741.
741.
395.
395.
345.
345. So what is the first step? Okay, yeah, so the first step is always to maybe calculate what is the determinant of A. What is the determinant of that? Okay, it seems to be a random number, so maybe you can do some real transformation a little bit to simplify that. So the determinant of 741, 395, 345. As you can see, you want to maybe you use the third row to subtract the second row. So the second row subtract by the third row, you will get some easy form. So 741, 0, 5, 0, and 3, 4, 5. And then you can expand that from the second row by Laplacian expansion. So this guy is equal to 5 times, what are numbers over there? Yeah, 7135. So this guy equal to 5 times, what is this number? Yeah, 32. So it's equal to 160, right? So you know that the determinant of A is 160. Okay, and what is the next step? The next step is to find the algebraic cofactor of each element, right? So what is capital A11? What's that? Calculating in mind. 25. Yeah, 25. Okay, A12. Yeah, okay. A13. 15? Yeah, negative 15. A21 is equal to
16. Or negative 16.
Actually, it is negative 16, right? Because you have to add minus sign in front of that. Because yeah, 4145, right? So it's 20 minus 4 is 16, but you have to add a minus sign over here because it is in the second row of the first column. So remember this table, right? So this guy should be negative 16. Okay, so A22 is equal to yeah, 32. A23 is equal to yeah, next is negative 16. Okay, so A31 is equal to yeah, 11. Good. A32 is equal to
32 negative.
yeah, negative 32. Okay. The last guy.
51.
Yeah, exactly. 51. Okay. Yeah. So, okay. Then what is the inverse? What is A inverse? Let me erase all of that. Ooh. What's that?
Don't steal the chair.
They just put a line in that in case that the chair might be stolen or not. Okay. What is A inverse? Tell me the elements each column by column. So
25
yeah, 25.
over
Uh-huh.
160.
Uh-huh. And you can simplify it as 5 over 32, right? This number?
0.
Yeah, okay, perfect. This number? Yeah, negative 15 over 160. You can simplify it as negative 3 over 32, right? You divide that both by 5. Okay, and this number? Yeah, negative 1/10. And this number? Yeah, 1/5. Okay. This number? Yeah, negative 1/10. That number? Yeah, 11 over 16. This number? Yeah, negative 1/5. This number? Yeah, 51 over 16. Okay, so this is an A inverse. From A, you have A inverse. And this method works very well for 2x2 and 3x3 matrices.
Can you give everything on the board like a name? Like, what is the full factor?
The name for this kind of method?
Or like what is that called? Or sorry, that's the inverse. So like, what's this called?
This one?
Yeah.
Okay, this one, if you transpose that is called algebraic.
Algebraic cofactor.
It
Oh, no,
just called
algebraic.
algebraic, and it's noted as A upper star.
Okay. And it's after you have already applied the plus
Transpose.
minus.
Yeah. Each of those guys is called the algebraic cofactors.
So the only thing missing from the algebra that gets you to the inverse is one over the determinant.
Yeah. You just get everything over determinant, then you get to the inverse of that. Okay, this is basically the method to find the inverse. And last time we introduced a little bit about what is linear equations and what is a system of linear equations. So this time we will concentrate on how to solve a linear equation, and I'll try my best to finish the chapter 2 this time. So let's see. What are these? Maybe this is a price of tutor every 1 hour. Okay. Okay, so linear equations. Okay, let's just start with examples. So let's look at this linear equation. Suppose I have maybe x plus y plus z is equal to 2, and maybe x plus z is equal to 3, and x plus y is equal to 0. Okay, can anyone make a guess that what is x, y, z? What is z?
2.
How can you do that? Because you know that x plus y is equal to 0, and here x plus y plus z is equal to 2, so this part is equal to 0, so it tells you z is equal to 2. Okay, and if you know z is equal to 2, what is x? 1. And if x is 1, what is y? -1, right? Okay, in this example, the solution here is unique. Because the number of z can only be 2, and the number of x can only be 1, and the number of y can only be -1. And as you can see, the last time I told you that there are 2 points of view to actually 2 points of view to look at what is linear equation. A linear equation, if you look at row by row, which means, so for this linear equation, you can associate it to a matrix like this 1, 1, 1, and 1, 0, 1, and 1, 1, 0. X, Y, Z is equal to 2, 3, 0, right? So if you look at each row by row of this matrix, which is basically means that by looking at each equations, and actually each equation corresponds to a plane in a 3-dimensional space. And then the geometric meaning for those equations to have a unique solution means that actually you have 3 planes in your 3-dimensional space, and they are actually in the most general positions that 3 planes intersect in a point, right? Okay, sorry. I should just draw the graph like 3 planes that intersect to a point. 3 planes intersect to a point.
Is it the number of variables or the number of equations that determines what dimension you're operating in?
Because you have 3 variables.
Okay.
Yeah. So, okay. And also in this matrix form, I only write 3 variables, so you can think everything happens in a 3-dimensional space. Okay, so in the row space, it means that these 3 planes, which correspond to each of the equations, actually intersect at a single point. And actually, if you look column by column, those x, y, z simply means the coefficient that you combine in each of the column of this matrix, and the goal of your combination is to reach this 2, 3, 0. So and the solution of this equation is unique. Basically, tells you that the only method to combine those 3 vectors such that they gives 2, 3, 0 is letting x is equal to 1, y is -1, and z is equal to 2. So actually, that basically tells you that those 3 vectors in the 3-dimensional space is not in a plane, right? So that means those 3 vectors are in very general position, such that if you give me a vector, I will have a unique way to combine them such that they could reach this vector. What I mean is that if they are not in a general position, which I mean is that if they are in if those 3 vectors is actually in a plane, right? If those 3 vectors in a plane, then you will have multiple ways to combine you will have multiple ways to do linear combination of these 3 vectors such that it could reach this kind of vector. Right? So we will talk about this case later. And in this case, the solution of that is unique. It basically means those 3 vectors is in general positions of 3-dimensional space, so that it can combine. It can give you a unique. Unique coefficient such that you got this vector. Okay, so let's continue to discuss about how can we find those solutions so quickly, right? So actually, the basic skill we use is actually to use this equation to do something on that equation. And this is a very like a row transformation, right? So think about how do you get z is equal to 2. Basically, you just use this method in your mind. Like x plus y plus z is equal to 2. And then you know that x plus y is equal to 0. So what you did actually is actually minus these equations on both sides, right? And then the final result would just be like z equal to 2 minus 0. So z is equal to 2. So this is basically what you did. And then you can use this equation to substitute the first equation. And it doesn't change the solutions because you just add each equations, and that doesn't change your solutions. So what is the analog of this kind of operation on this matrix? Yeah, it is just row adding, right? Because the operation to change this equation to this equation, which is z is equal to 2, x plus z is equal to 3, and x plus y is equal to 0. It's actually like row adding, right? So actually, how to get this from that is by add the first row by minus 1 times the last row, right? So what you get is actually 0, 0, 1, 1, 0, 1, and 1, 1, 0. X, y, z is equal to 2, 3, 0. Okay, so basically, as you can see, in this kind of interpretation, if we linear combine several equations together to substitute one equation, that doesn't change your solutions. And in the point of view of the matrix, the solutions of those equations is actually the coefficient in front of those three column matrices such that you want to combine to this matrix. So actually, this 3 coefficient tells you some linear relations on columns, and from this point of view, we can see this fact that the row transformation, the row operation does not change the linear relations on columns. So that's why it doesn't change the solutions on this point of view. And there's also another point of view that if you do row transformations, that is equivalent to, say, the left multiplying a matrix, right? So how do you get this matrix from that matrix? By left multiplying something. Can anyone tells me that? Okay, so what is this matrix equal to? 0, 0, 1, 1, 0, 1, 1, 1, 0 is equal to what matrix times 1, 1, 1, 1, 0, 1, 1, 1, 0? Can anyone tell me the element of this matrix will be column by column? Anyone can see that? Where is this element? 1,
0,
0, 0, 0, 1, 0, 0. Yeah, negative 1.
0, 1.
Okay. Yeah. So because we got this matrix by the row transformation of that, right? So that means this matrix is equal to this matrix multiplied with that matrix. So basically, what we did is actually to do this kind of row transformation, not only on those rows, but also on those numbers. So actually, if we write everything down, that means that means the solutions of these two guys are actually the same. And the solutions of this guy are actually the same. So why are they the same? Because we just left to multiply this invertible matrix on both sides of these equalities. So of course that doesn't change those x, y, z. So there are actually 3 points of view why if you do row transformation that would keep the solutions. Any question? Okay, because the row transformation does not change the linear relations on columns, or does not change the solutions of this linear equation. So we can basically reduce every matrix to what? To find the solutions of the linear equation. What do we want to reduce those matrices to? Yeah, we want to reduce that to the reduced row echelon form, because as we can see, if we do row operation, that does not change the solution. So the method of how we solve a linear equation is by reduce those coefficient matrix to the reduced row echelon form. So let's just see some examples Okay, maybe let's see example like this. Okay, let's do something maybe harder. 3x plus 2y plus z is equal to 10, and x plus y plus 4z is equal to 15. Okay. Let's look at how to solve these equations, right? So we have such kind of a system of linear equations. So basically, we write that in a matrix form. So like this: like 3, 2, 1, 1, 1, 4, and x, y is equal to 10, 15. And because of that, we want to do row transformations not only on this coefficient matrix, but also on this guy, right? On the 2, 3, 0, like the things that on the right of those equations. So basically, because we want to do row transformations of all of the guys together, so we put everything together, like 3, 2, 1, 1, 1, 4, and you write a dash line, and 10, 15. And then you can do the row transformations to reduce that to the reduced row echelon form. So what is the first that you want to do to reduce that to reduce row echelon form?
Should we put a z there?
Huh? Oh yeah, okay, I missed something. Okay, sorry. Sorry. Okay. What do you want to do over here? Reduce that to reduce row echelon form.
1 minus 2 is the second row.
The first row minus
2 is the second row.
why 2?
Because then
Why
you
not
get
3? 3. Because you want to kill something, right? So just kill it. Okay, so the first row minus 3 times the second row, right? So what we get is that, oh, maybe you want to kill this number, right?
Yeah.
Let's do your way back. Okay. If you do that, this is what is that? It's 1, 1, right? And 0, 1, and this is negative 7, 4, and this is negative 20, 15, right? Okay, so what is the next step? What do you want to do next?
R2 minus R1.
Okay, R2 minus R1. Okay, and then what you get is R2 minus R1, so this number is already killed. And R2 minus R1, 11, minus 7, minus 20, 35. Okay. So this looks 1, 1, 2, 3. Okay. Oh yeah. Okay. So this is a reduced direction 4, right? So this is the leading ones, and then you actually got those numbers, right? So basically, you are going to find x, y, z such that it satisfies the equations, and you know that this equation is equivalent to that equation, right? To x, y, z is equal to 10, 15. Okay, so what is x, y, and z? That's it?
Yeah. Why did you bother doing the thing on the right where it's like negative 20, 35, and you're just going to leave it as 10?
A typo?
You should have written negative 20 and 35.
Well, where it says 10, 15,
The bottom.
the bottom left.
And what do you mean here?
No, the bottom
No,
left.
it's over there.
Bottom.
On the other side.
No, other side.
On the other side. Lock, lock,
So
lock,
what's it?
lock. Keep going.
Oh yeah. Okay, yeah. Sorry. There are a lot of mistakes. Okay. So if you know that, basically that tells you the equation like x minus 7z is minus 20, and actually y plus 11z is equal to 75. And actually this is the simplest version of these linear equations, and you can actually solve that, right? So what is x, y, and z? So what is x, y, and z? Because you know that this x, y, z tells you what? Tells you basically the coefficient of each column, right? Such that you can combine to this kind of column matrix. So can anyone give me a value of x, y, z such that this equation holds true?
Z is 3.
You want it to be 3? Oh, okay, yeah, you can also do that. Z is equal to 3 and
Y is equal to 2.
y is equal to 2.
X is 1.
X is 1. Maybe, yes, this is a solution because as you can see, this is 1, 0 times 1 plus 0, 1 times 1 plus negative 7, 11 times 3 is actually equal to negative 20, 35. But it is not very clear to observe, right? How do you know that?
I figured out the first one first.
Okay, yeah.
One
But
minus
actually,
one.
this is not easy to observe. So there is also a solution which is very easy to observe, right? Because as you can see, you want to make linear coefficients of x, y, z such that if you multiply this column by x plus this column by y plus this column by z, you will get this. Okay, so what I mean is that as you can see, this is negative 20, right? So what do you want to do? You just multiply the first column by negative 20, and then plus the second column multiplied by 35. So there's also another solution which is x is negative 20 and y is 35. And then you don't want to make use of z, so you just set z is equal to 0. Right? This is might be the easiest one to observe by using the leading ones, right? Okay, so this is the example of how do we find at least one solution of this kind of equation.
Does this have infinite number of solutions?
Yeah, there are infinitely many solutions, and actually later on we will talk about how do we find all of that. But now at least we can get one of the solutions right over here. Like this. Question?
Can you explain again how you get x equal to -20?
Because by looking at this matrix multiplication, right? So what does that mean? What does that mean? You have this matrix multiplied that matrix is equal to -20, 35, right? And this basically tells you if you separate this matrix by this, right? Then this is the same as asking 1, 0 times x plus 0, 1 times y plus 27, 11 times z is equal to 20, 75.
Okay.
Right? So maybe the easiest way for you to make this equation to be true is to let x to be -20 and y to be 35. Okay. Any other question? Okay, in this example, as you can see, the solution is not unique. There, because we already have found 2, and in fact, it will have infinite many solutions. Just as you can see, because you only have 2 equations here, right? And actually, everything is in 3-dimensional space. This is just like each of the equation corresponds to a plane, right? So if you draw a plane over here and draw another plane, and then you will see that those 2 planes is actually intersect at one line. So it's not just only intersect at one point; it will intersect at one line. So because a line consists of infinitely many points, so that's why we should have maybe infinitely many solutions. And the easiest solutions that we found here is just one point, right? And later on we will study how do we find all other points. Okay, so this is the second one. It's not like the first one. For the first one, we have unique solution, but for this one, we have solutions, but the solution is not unique. And then I also tells you basically how do we find at least one of the solutions by reduce that matrix into this relation form, and then you just make appropriate coefficients such that these leading ones can combine out this column matrix. Okay, so we have already discussed 2 types. So there are also another type of linear equations which actually basically will have no solutions, right? So can you imagine geometrically when does that kind of thing happen? Yeah, if you have parallel planes, right, then it will have no intersect points. So basically, this example I'll do maybe example 3. Maybe I'll do something example 3. So it's like x plus 2y plus z is equal to 1. And suppose that x plus z is equal to 2. And now I say 3x plus 2y plus maybe 3z is equal to 6. Okay. And we are still using that method to see what is the solutions of this guy. Because as you can see, doing row transformation will not change the solution. So let's do that. The thing you write here is all the coefficients, 1, 2, 1. 1, 0, 1, and 3, 2, 3, and we together with 1, 2, 6, right? What is the first thing you want to do to reduce that to reduce reaction form? Suggestions? Okay. Which row?
First minus second.
Okay, first row minus second row. First row minus second row. You get, okay, so this is 0, this is 2, 0, minus 1, 1, 0, 1, 2, and 3, 2, 3, 6. Okay, what is next? Any suggestions?
Let's
What is-
just switch it first and second.
Yeah, you can do that. First row and second row, switch that. You got 1, 0, 1, 2, 2, minus 1, 3, 2, 3, 6. Okay. And then, anyone want to give a suggestion of what is next step?
R3 minus 3R1.
Yeah. Then you can clear the first column. R3 minus 3 times R1. You got 1, 0, 1, 2, 2 minus 1, and this is 0, 2, 0, 0. Okay, as you can see, here is already 0. And there's also, before you reduce to the reducer row echelon form, you will see some disaster already happens, right? Even before you reduce that to reducer row echelon form, even if you reduce to this step, you will see this equation is equivalent to say that 1, 0, 1, 2, 2, like x, y, z is equal to 2, negative 1, 0. And as you can see, those x, y, z actually tells you the linear combinations such that, let's see, is there any disaster happens? Okay, let's just continue row reducing, because it's hard to say the disaster at this time. I just want to say if this is equal to 0, then y could not be equal to negative 1. Okay, let's just continue about reducing rows. Any suggestion if you want to reduce the row of this matrix?
R2 minus R3.
Okay, the third one minus the second one, right? Okay, as you will see that 1, 0, 1, 2, and 2 minus 1, 1, right? Okay, I think now question?
Can we do R3 minus half R2?
Yes, you can. You want to do what? R3 minus half?
R2.
Yeah, you can do
So
that.
how do you put 1 at the bottom?
Yeah, you can do that, but okay, R3 minus half of R2, right? And then what happens is that R3 minus half of R2, you get this to be 1, you get this minus 1 half. 1 half.
So I wrote 2 by 2.
But what do you want?
R2 minus
Get rid of
2
R2. R2 minus 2R3.
Then R2 minus 2R3. Yeah, you can do that. Okay. R2 minus 2 times R3, right? Okay.
And switch the R2 and R3.
Yeah, okay. Follow your step. R2 minus 2 times R3, you get 1, 0, 1, 2. R2 minus, so this is 0, this is minus 2, right? Minus 2. And this is 1, 1 half. And then you want to switch those rows, right? Okay.
Would that be reduced row echelon form?
Yeah. We want to switch rows, right?
These are the columns.
Huh? 2, 1 half. R2 switch with R3. Yeah, this is already a reduced reduction form. Question? You mean this one?
No, don't you know there's no solution the second the row of zeros equals not zero?
Yeah, exactly. So that basically already tells you there's no solutions.
So we didn't need to.
Yeah, you didn't need to do that. Yeah, because that guy want me to reduce that everything to a reduced reduction form. So you can even predict the result even before you reduce to the reduction form. Okay, so I will use either of that to say something about this phenomenon. As you can see, this equation basically tells you that you reduce to that equation, which is x plus z is equal to 2, right? Okay, I have no space. So it reduces to the like x plus z is equal to 2, and as you can see, y is equal to 1/2. And the last guy tells you 0 is equal to -2. Okay, as you can see, what happens here? You have something that gives you contradictions. So any x, y, z will not make sense for this equation to be true. So this is an example that a linear equation have no solutions. Okay, so but how do we see this kind of fact in the reduced reduction form? As you can see, this is not exactly reduced reduction form because you still have to reduce this one if you want it to be a reduced reduction form. So -1/2 times the third row, you get 1, 0, 1, 1, and you get 2 into 1/2 and 1. As you can see, if you do all of that process and then reduce everything to the reduced reduction form, if in your last column, which is the column that recording coefficient on the right of the equation, if there is a leading one appears in the last column, then this solution, then this equation will not have solutions, because just because of that, in the last row, the corresponding equation is like 0 equal to 1, and this will make this phenomenon will make the system of these equations have no solutions. Okay, and how do we understand that using the matrix? As you can see, this system of linear equations just corresponding to a matrix like 1, 0, 1, 1, 0, and 0, 0, 0, right? Multiply with x, y, z is equal to 2, 1/2, and 1, right? And this basically asking you to find those x, y, z such that if you combine those column matrices, then you got this one, right? But there's no way to combine those column matrices to get this column matrix, because as you can see, all the entries of the last row is equal to 0. So no matter which x, which y, which z you use, you cannot combine out this result, because the last guy of this column vector of this column matrix is 1. So there are multiple ways to understand of this fact, and so as you can see, this kind of understanding is understanding from the columns. And what is the understanding of each rows, right? The geometric picture of this kind of equation is like this. It's like you have 3 planes, right? Right over here, and then you got another plane over here. You got another plane over here, and then you got other planes over here, and then it's just like this case. So you have something like this one, this one, this one. So like this one. So that they will have no intersections. Like all those 3 intersection lines are parallel each other, and then you will have no intersection points. So that is for these equations. Any question?
So like usually we solve the system equations by reduced row echelon.
Mhm.
Can you also reduce the columns? Or do that
Yeah, you can also reduce the columns.
Okay.
Yeah, but maybe because of the time, it's limited, so I will see that in the future or not in this class now. Any other question?
Well, I guess, we think the conflict is in the last row where 0 equals to 1.
Yeah.
But I guess you could also say the conflict is where, if you go up to brackets, where your hand is actually.
Here?
Y has 2 different values that could also.
Yeah, exactly. As you can see, y is equal to y. This tells you y is equal to -1/2, and this tells you y is equal to 0. So this is what I want to explain previously, and I think maybe this one is easier to see. Yeah, as you can see, 2y is equal to -1 and 2y is equal to 0. Then y have 2 conflict values. Then, that's why you will have no solutions for this system. Okay. Any other comments or questions? Okay. Just as you can see that for a system of linear equations, you could have a unique solution. You could also have infinitely many solutions, and you can also have no solutions, right? So there are basically 3 cases. So at least in the case that when those linear equations have solutions, we can use this method to find at least one solution, right? When we reduce everything to the redistribution form, and if the last column does not have leading ones, we can always use those numbers as the coefficient in front of each column to combine this column matrix. Just like this example, that you can use -20 as a coefficient in the right of this 1, 0, and use 35 as a coefficient in the right of 0, 1. And you observe a linear relation is the first column times -20 plus the second column times 35 is equal to the last column. And because the row transformation does not change the linear relations on columns, so this is also true for the most original one. So it is the same as saying the first column times -20 plus the second column times 35 is equal to this one. So which is basically means that x is if x is equal to -20, y is equal to 35. When this is equal to 0, tells you a solution. So basically, how do we find all the solutions? Because as you can see, some students says that there are also another solution. So how do we find other solutions? So basically, there's one observation that if I denote those 2 solutions as x1, y1, z1, x1, y1, z1, and x2, y2, z2, right? So what it tells you that they are both the solutions of these equations. So what you get is actually 3, 2, 1, 1, 1, 4, multiply like this chart. 1, 2, 3 is equal to 10, 15, right? And you also have 3, 2, 1, 1, 1, 4, -20, 35, 0 is also equal to 10, 15, right? Okay, because as you can see, you have 2 equations, and you have something which is the same on the left. So basically, here's the idea that you can take difference of those 2 equations. So which is basically tells you that so if you take difference of those 2 equations, that will give you 3, 2, 1, 1, 1, 4, 1, 2, 3 minus 3, 2, 1, 1, 1, 4 multiply with -20, 35, 0 is equal to what? 0, right? Is equal to 10, 5, 10, 15 minus 10, 15. So this guy should be equal to 0, right? So, and as you can see, there is something similar on the left. So you can check it out. So you have 3, 2, 1, 1, 1, 4. Like, you take a big bracket, and 1, 2, 3 minus -20, 35, 0 equal to 0, 0. And then as you can see, if you minus those two, this one will give you 3, 2, 1, 1, 1, 4 multiply with 21, -33, and 3 equal to 0, 0. So that basically tells you the fact that if you take any two solutions of these linear equations and you look at the difference of the solutions is exactly a solution of this linear equation. If we take, if we let each guys on the right to be 0, 0, right? So if you have multiple solutions for those guys, like this is a solution, right? This is a solution for this kind of equation. This is a solution for this kind of equation. You just simply add these two up, and then you will get another solutions for this kind of equation. So in linear algebra, we call this kind of equation as non-homogeneous. And this kind of equation, we call it as homogeneous. So non-homogeneous simply means that that the guy on the right is not 0, 0. Homogeneous just means for each of the equation, it should be equal to 0. So why it is called homogeneous? Because if you let x plus maybe 2, 1 plus z equal to 0, you can actually multiply each of the variables by a constant without changing the equation. Like 3x plus 6y plus 3z equal to 0. And you can also multiply by another number. It is just because of the fact that here is 0. If this guy is not 0, then if you just multiply the variables, that will change the equation because you also have to multiply the same scalar on the right. So the homogeneous simply means that because the guys on the right is 0, so you can just multiply each variable by the same similar without changing the equation. So that is basically what homogeneous means. So just remember the homogeneous guy is when the right number after each equation is 0. So this basically tells you if you want to solve the most general linear equation, which is non-homogeneous guy, the method is to solve out at least one solution, and then looking at the equations that looking at the corresponding homogeneous equations, and then find other solutions of these homogeneous equations, and after that you just add each of the solutions on the one of the solutions you get. Like in this example, you have a solutions like this, right? Like you have a solution. So you already have a solution like 20, 35, you're over here. And you have solutions for this is non-homogeneous. And then here is homogeneous. Okay, so you have one solution, negative 21, negative 33, 3 over here. You can also have another solution which is 42, negative 66, and 6 over here. You can also have another solution which is like 63, negative 99, and 9 over here, right? And if you add each one of them to the original guy you observed, you will finally give many solutions of these non-homogeneous guys. So for this one, it's 1, 2, 3, right? And for that one, if you add it up, it will be 22, negative 31, and 6. And if you continue add this one to that one, you will get actually 43, negative 64, and 9, right? So everything here is actually solutions for these non-homogeneous equations. Right? Because the reason is very simple, because if you name this matrix as A, right? And A times this matrix will already give you 10, 15, right? And A multiplies each of those guys gives 0, 0, 0, right? So it means that no matter which guy, no matter which one you combine this to that, the thing on the right is always equal to this 10, 5 original guy combined with 0, 0. So it is still 10, 15. So that's why by adding solutions of the corresponding homogeneous equations will give you another solutions. And the reverse is also true. Any two solutions of a non-homogeneous equations, the difference is the solutions for the corresponding homogeneous equations. So that basically tells you the fact that all solutions is actually equal to at least one solution for homogeneous. For non-homogeneous, n plus all solutions for homogeneous guy, right?
Why not say all solution for non-homogeneous as well?
All solutions for non-homogeneous equations.
Like, instead of the one solution for non-homogeneous, why don't we say all solution for non-homogeneous? Because there isn't just one solution.
Yeah, it isn't just one. I mean, every solution, to find every solutions of the non-homogeneous equation, you should at least find one solution first, and then combine with all the solutions for the corresponding homogeneous equations. Any other question?
Can you explain again the point why you add up like homogeneous solution?
To the non-homogeneous solution, you get another solution of the non-homogeneous solution.
Yeah.
Okay. Yeah, this is because of the fact that if I let this matrix to be A, right? Then A times this one gives you 10, 15. And A times that one gives you 0, 0. So if you add those two solutions together, and sorry, I just brought up space. Because you know, let's just put one of them. Because you know that A multiply with this column matrix becomes 0, 0, right? 0, 0. And A multiply this matrix gives you 10, 15. So simply add those two equations together. Right? So if you add them up, you will get A equals 20, 35, 0, plus A multiplied with 21 and 33, 3 equal to 10, 15 plus 0, 0, right? This is correct, right? And then the next step is that you just factor out this A and combine those two column matrix. So what we get is A 1, 2, 3 is equal to 10, 15. And this is exactly means that 1, 2, 3 is a solution of this A x, y, z equal to 10, 15, right? It is just basically because of the fact over here. it is 0, 0. So no matter how many 0, 0 we combine with 10, 15, this 10, 15 will still become 10, 15. Question?
When you say homogeneous, do you mean the equations are homogeneous or the matrices are homogeneous or?
I mean, in a matrix, homogeneous just means that this part is equal to 0, 0. I mean, the equation is homogeneous.
The equation is
Homogeneous linear equations. So it is a word that say something about the equations.
So which equation and which equation are homogeneous?
So if this equation is not homogeneous, this is not homogeneous. I mean, if I write 0, it's homogeneous. So homogeneous.
So if the equation is equal to 0, then it is homogeneous.
Yeah. And if not, we call it non-homogeneous. And for a system of equation, we call it homogeneous if all the guys on the right is 0. So I mean, every equation in the system is homogeneous because the system is homogeneous. Any other question? Okay. Yeah. So far, so good. So as you can see, we already talked about the method to find at least one solutions for non-homogeneous equations. And in order to find all other solutions, we should study how to find all solutions for homogeneous equations. So this is our next topic, is solutions of homogeneous equations. So basically, a system of homogeneous equation just a bunch of linear equations in which each guy, the constant on the right of the equation is 0. So for example, this guy has like x plus 2y plus z equals 0, and y plus z is equal to 0, and maybe x plus y is equal to 0. So this guy is called a homogeneous equations. So can you tell me maybe at least one of the solutions of this equation?
0, 0, 0.
Yeah, 0, 0, 0. Because as you can see, 0 equals 0, right? So for the homogeneous equations, the solutions always exist, right? So at least one solution for homogeneous equations is that you can set all variables to be 0, and this is a solution for this homogeneous equation. So actually, the thing we want to do is to find all the solutions of the homogeneous equations. So actually, the way we do that is the same as the way that we did on the non-homogeneous equations, because as you can see, the reduced row, the row operation does not change the solutions of the equations. So we can actually reduce everything to the reduced row echelon form. So like this, right? The thing you want to do is like you write you just write every coefficient in the matrix like 1, 2, 1, 1, 1 is over here, and 1, 1 is over here. And because as you can see, each of those guys is all the 0, so you don't have to put a dash line and to write 0. Because even if you write like this form, if you do row transformations, those guys will still keep as 0, 0, 0, right? So you don't have to write the last column. So you just do the row transformations on this matrix and reduce that to the reduced row echelon form. Okay, so what is reduced row echelon form after that? as you can see that this 1, 2, 1 can be just viewed as a combination of the last two rows, right? So I can do maybe I'll do the first row minus the second row, and I got 1, 1, 1, 1, 1, 1, and then I just want to use the last row minus the first row, and then I got 1, 1, 1, 1. Or maybe, 1, 1 on the top, 1, 1. And then I'll just continue doing this kind of stuff. Like, okay, I want to use this one to clean up this one. So R1 minus R2, what you get is 1, 0, minus 1, and 1, 1. So this is already a reduced row echelon form, right? It's right over here. Okay, so finally, what is the equations looks like? What is the corresponding equations? X minus d equal to 0, and then y plus z equal to 0, right? And as you can see, we actually want to find all the solutions of these homogeneous linear equations. So that means we are not satisfied by only find one of them. So how do we find that? As you can see, we can make some parameters. So actually, we can let z equal to, as you can see, we can actually let z equal to t, right? Let z equal to t. And if z is equal to t, then xy could be expressed as a linear combination of just this guy, right? So if z is equal to t, what is x? Yeah, x equal to t because of x minus z is equal to 0. So what is y? Negative t, right? Yeah. So basically, all the solutions for this homogeneous equations is that x is equal to t, y is equal to negative t, and z is equal to t, where t could be all the real numbers. So that means basically whenever you give me a number of t, I can just plug in t to all of that, right? And then I will get a solution. And this guy could also written as x, y, z is equal to 1, t, 1, 1, t. Right? So these are all the solutions. Why are they all the solutions? Because, as you can see, I already assume that z is some number. Z is some number that I unknown. Because I don't know this number, so I just assume this number to be t. And after I assume this variable is equal to t, then any other variables can be uniquely expressed as expression of t. And in this way, I claim that I have already found all the solutions because I only use one parameters, and then the values of x and value of y is uniquely determined by the value of z. Any other question? Okay, look at why do I let z equal to t. This is simply because of this column. So after you reduce that to a reduced rational form, you just use the variable in which this variable corresponding a column that is that does not contain leading one, and then you name and then you let this variable to be equal to t, and then you can express other variables which have leading ones as an expression of those variables. maybe the sentence is not clear, but I will give you another example. Right? I'll give you another example to make my statement clear. So let's just suppose that after reduce a homogeneous equation, I got an equation like this. Maybe the reduced rational form is like 1, and here's 2, and here's 1, here's 5, 3, and here's 1 over here, and here is 3, 2, 1. Okay. And suppose that my variables are x, y, z, a, b, c. Okay, it's equal to 0, 0, 0. Okay, so tell me which variable that you want to assume it to be some parameters. Compare with the guy that I did over there.
C.
C.
No, A.
A.
Y.
Y. Because these three variables corresponding to those columns that does not have leading ones. Right? So this guy corresponds to Y, this guy corresponds to Z, this guy corresponds to C. And then the next step is that you can let this variable to be like y is equal to t, and then z is equal to w, and c is equal to u. Okay, and look at what it is. What each of the equation tells you. So the first equation is
You meant A, not C.
oh yeah. Thank you for this. Why are you listening? Sorry. Okay, why do I want this? Because as you can see, if you look at this matrix, each row by row, the only thing that will appear in each of the equation is the guys that does not have is those guys who does not have leading ones. So each of the equation only have a variable which have leading one together with other variables that that correspond to the columns which does not have leading one. So this is why I want to just give a name for those variables, and those variables is actually called free variables in the homogeneous linear equations. And then I just give parameters of each variables right over here. And then I just take a look at each of the equation again. So what is the first equation? The first equation is x plus 2y plus 3a plus c equals 0, right? Because you just multiply the first row by that. So, and then you can actually move everything to the right. So which means x is actually basically equal to negative 2y minus 3a minus c, right? So what is x equal to if you use t, w, and u? Yeah, x is equal to negative 2t minus 3w minus u.
How'd you get 3 equals C?
Huh?
How'd you get 3 equals C?
C equal what?
The x plus 2y plus 3 equals C equals 0.
Yeah, x plus 2y plus 3a plus c equals 0.
Why is that? Oh, sorry.
What I mean is by looking back to each of the equations, you can you will know each of the variables in terms of t, w, and u, which is the parameter that assigned to each free variable. And each free variable comes from the columns that does not have leading one. Okay, and this time that you can actually use the first equation, because every equation only have one variable which corresponding to leading one, and all other variables are those variables that corresponding to the columns that does not have leading ones. And I already give each variables that correspond to the column which not have leading one to a parameter like this. So actually, for each of the equation, you can move the terms that corresponding to the columns that does not have leading one to the right hand side, and you will express the term that corresponding to the leading one to the terms that corresponding to those columns, which is called the free variables, right? So you can express x as a linear combination of free variables, and because I already assigned each free variables a parameters, so x is equal to this guy. X equal to negative 2y minus 3a minus c equal to negative 2t minus 3w minus u. Okay, and how do we, okay, let's use this method to find the value of z. So what is z equal to? So tell me the equation first. Z
Plus 3c.
plus 5a plus 2c equal to 0. And then what's move which two terms to the right? Yeah, AC. So z is equal to negative 5a minus 2c, right? And finally plug in those variables, plug in those parameters, right? So this guy is equal to negative 5w minus 2u. Okay. Yeah, so this is z. Okay, so how about the last guy, which is b? So b is equal, okay, so which is the last equation? B plus 3c equal to 0. So b is equal to negative 3c, which is equal to negative 3u, okay? Okay, finally, you already expressed every term. You already expressed every variables in terms of t, w, u, which is I told you, right? So afterwards, you can write the solutions as okay. So like x, y, z, a, b, c equal to, you plug in all of these values over here, right? So as you can find that x is negative 2t minus 3w minus u, negative 2t minus 3w minus u. And then y is equal to t, right? Because y is already assigned by t. And z is equal to what?
Minus 5a minus 2c.
Yeah, minus 5w minus 2u, right? Because we want to give parameters, right? Minus 5w minus 2u. And then what is a? What is a equal to? W, okay. What is b equal to? Minus 3u. What is c equal to? U, okay. Just make sure you guys are not fall asleep. Okay, and then we actually can split this up by the linear combination of 3 column vectors. As you can see, if you only look at the term of t, then you can split it as negative 2, 1, 0, 0, 0, 0 multiplied with t, right? Because I want to put these terms here, right? And then if I ask you the column vector that in front of w, what are all those coefficients? Negative 3, 0, -5, 1. Okay. Okay, so how about this u? -1, 0, -2, 0, -3, 1. Okay. So basically this tells you all the solutions of the homogeneous equations. So all the solutions is like this. As you can see from this point of view, all the solutions of a homogeneous linear equation is actually a linear combination of those three guys, right? And each of these guys actually corresponding to a free variable, which comes from a column which does not have leading ones. So the column which does not have leading ones is free variables. Like this y, a, and c are free variables. And so for each of the free variables, you can actually you can think this column as if that you are plugging t equal to 1, w equal to 0, u equal to 0. So which I mean if you let t equal to 1, w equal to 0, u equal to 0, then the solution you get is -2, 1, 0, 0, 0, 0, right? And if you let t equal to 0, w equal to 1, u equal to 0, then the solution you get is like this, like this, right? -3, 0, -5, 1, 0, 0. And if you let t equal to 0, w equal to 0, u is equal to 1, you get these column vectors. So actually, as you can see, you can actually think all the solutions of homogeneous linear equations as a space. But I didn't tell you what is space. But okay, so as you can see, there are 3 parameters. So it is actually 3-dimensional, right? So basically, the dimension just tells you how many numbers that you need to determine a point in this space. So this space is 3-dimensional, which means you have 3 freedom of each variables. So basically, these are all the solutions for these homogeneous linear equations. Okay, so actually, this is a method to find all the solutions of the homogeneous linear equations. Okay, now let's think about this question. So when does a homogeneous linear equation have unique solution?
0.
Solution 0. When does the 0 solution unique?
Point.
When when you don't have free variables, right?
Yeah.
So in which case that you don't have free variables?
You have floor, right?
Every factor.
Okay. Can you just say?
Like you can get the reduced
Yeah.
fraction of the form, right?
Yeah, no. So in which case that you don't have free variables? It means that each leading one is actually occupied each columns, right? So it exactly means that your matrix is like the reduced direction form of your matrix is unit matrix, right? If the reduced direction form of your matrix is not unit matrix, you can always find some columns that does not have leading ones, which means you have free variables. So this basically means that, okay, if we call this matrix as coefficient matrix, that basically means a homogeneous equation have a unique solution if and only if the coefficient matrix is invertible, right? Because if you have a matrix that have reduced directional form equal to the unit matrix, that means this matrix is invertible. So,
Sorry, could you say all that again?
Yeah.
okay, I'll say everything again.
Not everything.
So my question is, when does a system of homogeneous equation only have unique solutions? So as you can see, the unique solution should be 0, 0, 0 because it should have the solution at least at least one solution like 0, all the guys 0. As you can see, the way I set unique, because I already, for each of the system of linear equations, I already explained that the solutions can be written as this form, and each of those free variables actually correspond to a column of the reduced relation form which does not have leading ones. So in order for a system of linear equations, of homogeneous linear equations to have unique solutions, the only way we can do is to write the matrix such that the reduced row echelon form does not have free variables, right? So does not have free variables simply means that each leading ones have already occupied all the columns. So which means the reduced row echelon form of A is equal to the identity matrix, right? So if the reduced row echelon form of A equal to the identity matrix, then A is invertible. Why is that?
Can you repeat the question?
Can you repeat? My question is, when does a system of homogeneous linear equations have unique solution? Okay, and okay, explain 3 times. Okay. Yeah, this part is important, so I'd like to explain 3 times. Okay, so as you can see, I already written all the solutions of homogeneous linear equations like this, and all of those indeterminate guys comes from free variables, and each free variables correspond to those columns which does not have leading ones. So in order for the set of all the solutions to be one point or to be just unique, then you don't need those variables, right? So which means you don't have t, you don't have w, and you don't have u, because if you have one of them, then you will have infinitely many solutions, because you can let u to be 1, 2, 3, 4, whatever you like. So the only way for a solution to be unique is to let the reduced relation form of the coefficient matrix, I call this as A, such that it does not have those columns which does not contain leading one. So this means that in order for a system of homogeneous linear equation to have unique solutions, then all those leading ones should occupy each of the columns. And just think of the reduced relation form. If the leading one occupied each of the columns, the only case that it could be is the unit matrix, right?
Or the identity matrix.
Identity matrix.
Are they the same thing?
Huh?
Are they the same thing?
Are they the same thing? Yeah, it's the same thing. Unit matrix is identity matrix is all the ones in a diagonal. Question?
Also, so like as long as all the columns are occupied by leading one, then it would be only one solution.
Yeah. Yeah.
Because there's no free variables
Yeah, means there's no free variables.
and no degrees of freedom.
Huh? No.
So the coefficient matrix is invertible.
Yeah, so the coefficient matrix are invertible matrix. Yeah, so if I reduce the relation form of A is equal to identity, then A is invertible. Everybody understand this or not? Why is invertible? Because the elementary row transformation is invertible, right? And the reduced relation form of A is actually obtained by doing some elementary row transformation, which means this reduced relation form of A is actually equal to PA, right? Which is in which P is an invertible matrix, and then PA is equal to identity. Then P is just the inverse of A. So that's why A is invertible.
But just because the matrix is invertible doesn't mean it will have a unique solution. Like, it's not a sufficient condition, right? Because you can have a matrix that's invertible and yet have many solutions.
don't think so. If you okay. Okay, that's
Awesome.
no.
Sorry, I'm just a little confused. Why does that have to be a unique matrix instead of just say it has a floor rank?
You mean
For the
oh yeah,
coefficient.
yeah. You mean this like this one?
Is it? Yeah.
Oh yeah, yeah. Okay, this x y z equal 0, 0, 0.
So it doesn't have to.
Oh yeah, yeah. Okay.
It just has to have.
Okay, so yeah, this point is correct. Sorry for that. Okay, so if a system of linear equations, if a system of of a homogeneous linear equation only have a unique solution, then the rank of then we have to require that the rank of A should be equal to the number of columns. Right? And this is this condition corresponds to that the this condition tells you that A is full rank on columns. Right? And actually if I add a condition that the if I add a condition that the number of the variables is at most the number of the is at most the number of the equations, then A is invertible, right? So okay, thank you for this this remark. Okay. So any other question?
So it's not when it equals the identity matrix?
Yeah, yeah, it's not.
Okay.
Because I just missed a point. Okay. What's the time is now?
47.
Okay. I still have 7 minutes. Since I can't finish this chapter, but
So like. But that's not. Well, depending on that. Yeah, so you can have sort of. Yeah, it's only dynamic chances when square. And the unit matrix is a Lorentz transform. Yeah.
okay, so a system of homogeneous linear equation has unique solution if and only if that the rank of the coefficient matrix equal to the number of the variables. So this is the proposition that I want to say. Actually, A is invertible is only a necessary condition, but not sufficient to. It's